Yeah, last but not least, I want to talk about some experiments that we run using Tamiflex and also the results that we obtained. And yeah, the results of the evaluation can also be read up in more detail in our ICSI paper that I already talked about. So first of all, one question that we also got from reviewers when we actually first submitted this to a conference. I don't remember to which one, but we first actually submitted it not to ICSI but somewhere else, and the paper got rejected. And one of the main questions that reviewers had, and it's an obvious question, right? So how can this be sound, right? And the point that we then made a bit more explicit in the second version of the paper that eventually got published was that it's not, right? So it's not a sound solution. It's not, in particular, not a complete solution, but it's sounder, right? So our argument is it's better than what people had before, and it's significantly better, although it does not solve the entire problem. And we actually also came up with what I think is a pretty sensible definition. And I already alluded to this earlier. We said that it's actually representative. So that means the following. If you have a sort of recorded call graph, right? So let's say if you were to execute a number of dynamic program runs, and during these program runs, you were to record the dynamic call graph, right? So the calls that are actually made at runtime. Then if during the same runs you were to use the playout agent, and you were then to construct a static call graph based on the information that you get from the playout phase, then this static call graph should be a superset of all these dynamically recorded call graphs. Okay, so that means your static analyzer, it's at least as complete as what you recorded at runtime. It covers at least those execution traces. And the question was, is that actually really the case? And in order to assure this or assess this, we computed static call graphs with Tamiflex and Zoot and Spark, so with this enhanced variant of Spark. And we also recorded dynamic call graphs with a JVMTI agent. So JVMTI is yet another instrumentation technology for the JVM, opposed to Tamiflex's implementation, which is entirely based on Java. This was actually implemented using C, so that's a C-based interface. Was a pain to implement it, let me tell you. But the advantage is that using this, you get even better call coverage. So here, the Java-based interface was good enough to instrument what we needed for playout and play-in. But here, this interface, we needed to really record every possible call that the JVM is really doing at runtime. And what we found out in our experiments was that, yes, this holds. So we really do get this guarantee that the static call graph contains all the calls that are made at runtime. In fact, it's not entirely true. Let me tell you an interesting story. So there was one single exception that I found interesting and funny. So what I didn't know before was that any program's main method, so the main method that is invoked initially by the Java virtual machine, that is also invoked using reflection. I didn't know this. I don't think anybody really knew this except for maybe the Sun or Oracle developers back then. But this actually showed up in the recordings of our JVMTI agent. So we always saw this initial reflective call to the main method. And that was not, really part of the Tamiflex log files. It wasn't showing up there. But it doesn't really matter because the main method is being considered as an entry point by the static analyzer anyways, right? So that wasn't really important. So in the end, this actually holds, and that means that the call graphs are representative. But another interesting question is, how effective is this approach, right? So how much does the logging file quality actually depend on the program input? And that's a perfectly legitimate question, right? So do we really need full code coverage or maybe even branch or path coverage to actually cover these portions of the program that really matter. And in order to assess this, at least to some extent, we did the following experiment. So I told you that we used this DACAPO benchmark suite, and DACAPO has these, I think, 12 different benchmarks here, right? They were all part of the same benchmark suite back then. And they all come, or at least most of them, come in 3 different configurations. So they have 3 different runtime parameters. One is called small, one is default, one is large. And so depending on these parameters, these benchmarks really execute differently. And what you see here is really the number of different call graph edges, so reflective call edges that were actually found for these different configurations. And you see some interesting results, right? So there are benchmarks such as H2, where the configuration doesn't matter at all. So no matter which input you choose, at least out of these 3 inputs, you always get the same reflective call edges. There are configurations where you see drastic differences. For instance, we looked into Jython, which is a Python interpreter, which also has some just-in-time compilation activity. And we saw that in the small configuration, there's no just-in-time compilation, but in the medium or default and large one, there is. And so there were a lot more classes loaded in these 2 configurations here than in the small one. Interestingly, we also saw such effects here. So there's a configuration that is called large for Aurora. And it is large because it's, exercising the benchmark with a larger workload. So the benchmark is doing more and it's taking a longer time to terminate its run. But actually, this is loading fewer classes than the small and default configuration. And you can see, similar other effects also for the other benchmarks here. Eclipse I already talked about. So there's a small configuration where the Java Development Toolkit is not loaded, the JDT, but in the default and large configuration they are loaded. And so that's why you see this hike up here in these numbers. So these configurations, they really matter, right? And yeah, I already talked about this. Then we also looked into this a bit deeper. We also wanted to see which of these call edges are actually really shared by these different configurations, because that's not really shown in this diagram, right? We only show the bare numbers, but you can't really see which of these, for instance here, right? Like these 36 edges, are they really the same, or is it just accidentally the same number? But you can see this here, right? And so, for instance, for Aurora, you can actually see that in these different runs, there are actually 5,000 cases that are common between large and small and default, but there are also a number of cases where this really diverges. And what was really nice now is that because DACAPO actually has these fixed configurations, this now actually allowed us to safely use static analysis on DACAPO. So for DACAPO, we can record for all of these different configurations the complete log files, and we can use them, and we get really sound results that are representative of these program runs. So that means even though Tamiflex maybe doesn't solve the whole program in its full generality, it did solve a really substantial problem for the community back then, because before this paper, people were really not able to use DACAPO for static analysis in a sensible way at all, because basically they would miss a lot of the functionality, right? So here for Jython, you would see that actually a lot of the functionality would be missed if you simply don't use any modeling of reflection at all, right? And now using this feature or this feature set that TamiFlex has, we really made da capo analyzable to static analysis. We also applied TamiFlex to other prominent programs and frameworks. So we ran it over another version of Eclipse, but also other programs that were known to use reflection. And we also found that for these programs, yes, the program inputs, they matter. So here, all of these lines here that you see are different configurations of these programs with different inputs. For PDF-SAM, the input didn't matter a lot, but for JEdit, for instance, the input did matter quite substantially. But there were also some cases where we saw that there were bigger jumps here, right? So for instance, here, if you loaded the Java Development Toolkit or the AspectJ Development Toolkit, there were significant increases in the number of these different reflective call edges that we saw. Here in JHotDraw, which is a Java-based drawing editor, if you use the full screen feature, that actually caused many more, classes to be reflectively loaded and reflective calls to be issued. In JRuby, if you use the UI with the swing, that actually caused a hike in the numbers. And so this somewhat told us that at least for some applications, you probably do not need full code coverage. You might get away with something like feature coverage, right? So you do need to cover substantial features in your playout runs, but then maybe the individual, properties of these runs, they don't matter that much anymore. Another interesting question that we also, of course, got from reviewers was performance overhead, because we're doing all of this runtime or load time instrumentation and runtime logging, and reviewers were asking us, okay, but how much does this cost? And what you can see here is that in general, play-in is rather cheap. So in the worst case, we saw an overhead of about 12%, which is, well, maybe not negligible, but it might still be acceptable in many cases. Also, play-out was rather cheap in most cases. But we saw two outliers where numbers were a bit worse. So one was FOP, which is relatively compute intensive, and one is trade soap. One outlier is trade soap. So I was really worried about this one, but then we looked into this deeper. So that was actually very interesting. So what is the problem? Remember that doing playout, we are also interested in recording the particular code location at which reflective call is happening with a line number. And the only way, at least back then, to actually create this information at runtime, at where am I currently in the program, at what line number, is using a stack trace. And we really created an exception object and extracted its stack trace. And this can be very expensive because the virtual machine then has to walk the entire stack. And in the case of trade soap, we had the problem that the stack was actually very large. So trade soap has a stack depth of oftentimes more than 250. So it's a very substantial program that has substantial use of frameworks and so on. And so we not only had large stacks to walk, but only this also this was done very frequently. So every few milliseconds or so. And then this slowed down the application significantly, like you saw here. I think by now there might actually be faster APIs to do this. I'm not entirely sure. So maybe this wouldn't even be such a large problem anymore. But in any case, this was really an exceptional case, I think. So it was really an outlier. And so it has not held back people from using TamiFlex in many other situations, at least not in an academic context for running experiments. Yeah, this also brings me to the summary of my presentation of TamiFlex altogether. So I showed you that call graphs are important to determine interprocedural control flow and that we must be aware of reflective calls. And I talked about the playout agent that records actual calls at runtime along with the classes that are actually loaded at runtime. We talked about the booster that sort of materializes reflective calls as normal method calls in the program binary. And then I also talked about the play-in agent that can be used to load transformed or instrumented or optimized classes back into the original system, into the original virtual machine. Now, TummyFlex is one very prominent dynamic approach to deal with reflection in static analysis, but there are other approaches. And if you're interested in these other approaches as well, I encourage you very much to take a look at this paper by some colleagues of mine that looked into how do actually static analysis themselves deal with Java reflection. So over the past few years, there have been quite some efforts in the static analysis community to also have static analysis deal with reflection better in a purely static fashion when it can be done, right? So like I said, in many cases, for instance, these string constants that I showed you, they are part of the program and they can be extracted by the static analysis. They can be made sense of. And Suit has some limited support for this, but also in particular, Dupe and also other frameworks have some limited or sometimes also even better support for this. Of course, this is always limited by what you can do statically, right? So if you know, these strings are loaded from some obscure file locations, or they are in a complex fashion dynamically constructed, then the static analyzer might not be able to make sense of it. But this paper here gives you a very good overview of what the different static analyzers do or do not support. At least back then in 2017. This might have still changed a little bit afterwards, but I don't think that you know, huge changes have been implemented since then, because in the end it's still an unsolvable problem. And really the only solution that you do have in the end, if you want to have some guaranteed coverage, is an approach such as TummyFlex, right? So with TummyFlex, you do get this guarantee of representativeness, and the static analyzer, well, it can still give it to you to some extent, maybe right by warning you if it was unable to resolve a certain reflective call. But then the question is still, what do you do about it, right? And then you might still have to resort to some dynamic recording. Yeah, so this should have given you some comprehensive coverage of the question of what to do with reflection in static analysis. I hope you enjoyed it. And next time you're using static analysis to actually analyze a real-world program, be aware of reflection and be aware of the fact that you might need to deal with it. And now I've shown you some options of how to do this. Yeah, I'm looking forward to speaking to you again next week. See you then. Bye-bye.